Okay, so now then let's take this to work through two examples, or let's apply this to two familiar operators. And so let's first do our first example, and let's talk about the momentum operator. We'll introduce some notation. Let's say, let's denote the eigenstates of P as Fp. And so meaning that if I apply momentum operator on Fp, that this is equal to P Fp. Okay. And then, no, Fp is going to be represented in real space Fp of x in real space. So there's some real space wave function associated with that. And the question is, what is Fp of x actually? Well, in real space, the eigenvalue equation, takes a familiar form. In real space, I'll use that my momentum operator is actually equal to h bar divided by I times the spatial derivative. And so my eigenvalue equation becomes, gets this form. And we know what the solution to this equation is. The solution is that Fp of x, so the real space representation is actually just given by the plane wave. And so this is the same as the plane wave solutions that we encountered when we discussed the free particle. Which makes sense because what we now also very clearly see is that the plane waves are states with well-defined momentum. They are eigenstates to the momentum operator. A problem with these states is they can't be normalized. And we've discussed this several times. But they do fulfill something that we call Dirac orthonormality. And that refers to the following property. If I take the inner product of two of these plane wave solutions, I get, the prefactor absolute value squared. I'll have to integrate from minus infinity to plus infinity e to the I pi. That's right, minus p1 x divided by h bar dx. And we know that this is actually proportional to the delta Dirac delta function using that delta of x is equal to 1 over 2 pi times integral minus infinity e to ikx. Okay, or if I wanted to now, maybe I should actually write it as or I can likewise write this just renaming variables. Can also write that this is equal to delta of k minus infinity plus infinity ei kx dx. If I use this, I get that this integral is equal to a squared times 2 pi times h bar. The h bar comes in because it's down here, and k is related to p through p is equal to h bar to k, and so I get delta p2 minus p1. And so if we choose a to simply be equal to 1 over square root 2 pi h bar, we get a nice relationship for the eigenfunctions of the momentum operator. Just like this. Okay. And this property guarantees that we can write any function in terms of the eigenstates of the momentum operator. With this property, we can write any psi of x, any real space function. We know this. This is actually, we know this from Fourier transforms that, this property guarantees that we can actually write any real space function in this form, or in our new notation, of course, we would write it like this. And let's put a dash here just to keep things clean in a moment. We can decompose any quantum state psi in terms of the momentum eigenstates. And then the function c of p dash is given as the inner product of fp psi. Let's double check that this is true. Let's check this. So fp with psi is equal to minus infinity to plus infinity. Let's see, p dash fp dash. We've just observed that this is equal to delta p minus p dash, and so yes, if we use this, then this is indeed equal to c of p. So what we've shown is that this property here guarantees that this is correct and that we can do this decomposition. Okay, so then just as another remark, of course, I can write this then also as I can write this inner product also as 1 over 2 square root 2 pi h bar minus infinity plus infinity e to the minus I px divided by h bar times psi of x and then dx. So, nothing too surprising. All this is just looking again at Fourier transforms. And now